This is the 19th video in a sequence on single agent search, and this video is going to be on external memory search. And in this video, we're going to be looking at the principles of external memory search, and then we'll be looking at a few sample algorithms. And the idea of external memory search is basically, if we think about running A star does duplicate detection, and then tries to solve really large problems, is that A star will run out of memory. And even if my computer maybe today has 64 gigabytes of memory, if I had something large, or maybe even something larger than that, we're still going to run out of memory fairly quickly, and we're not going to be able to solve really, really large problems. And so there's two things we can try and do with memory. In a couple of videos, we'll start talking about how we can build better heuristics. But the other approach is to say, to use external memory that is disk, to try to store states that we cannot fit in memory or cannot use in memory effectively. And one of the some of the key principles here is that random access. So if we think about when I'm trying to look up states on an open list or on a closed list or something like this, this generally requires random access. And so random access is fast in RAM and slow on disk. Now, although we'd say this is generally true, if you look at, for instance, even the cost of accessing RAM versus accessing a first level cache, RAM is orders of magnitude slower than a first level cache. But this is the first principle we're going to use because even RAM is orders of magnitude faster than disk. Solid state drives, SSDs, they are a little bit faster in that you could actually run with them. And we were, a number of years ago, I was able to measure the difference. And maybe they're only 10 to 50 times slower than RAM for some of the work that we were looking at the time. And so, yeah, SSDs help with this, but they don't completely solve the problem. And the more memory we have, the more RAM we have, the more it looks sort of like disk. So this idea is if we want to use a really large amount of memory, we're not going to be able to do random access. And this is the real key thing, is we need to avoid random access. So that's sort of the first principle. The second principle that we have to think about is the key thing that actually makes search difficult for particularly external memory search, but even if we look at something like A star. So just to say, IDA star can solve really large problems, but it can only do it if there aren't duplicates. And if there are duplicates in IDA star and we can't use some technique to discover those duplicates and remove them, then IDA star is going to have poor performance as a result and could be exponentially worse than you'd want it to be. Or then an A star search could be where we do duplicate detection. So duplicate detection is one of the reasons why we're doing a search where we'd want, when we want to do a really large search. And so duplicate detection is sort of the key thing, at least in heuristic search, is one of the key things that we want to look at or think about with respect to doing external memory search. So that's the key operation. Now there's a number, I guess I should say external memory search means instead of using main memory, we're going to use disk. So it could be a spinning disk or it could be a solid state drive. And there are a number of different fields that look at this different technology. I'm going to be presenting this from the perspective of search, like single agent search, in the perspective of this course. And so the other thing we can think about is, so when we're thinking about duplicate detection, we're going to think exclusively about undirected graphs. Or at least we're looking at undirected graphs where we know where the successors of a state are going to be, and the successors and predecessors are sort of equivalent or symmetric operations. Okay, and so that's just in this lecture. Okay, and now what we want to think about is, suppose we're doing a search, and there's going to be a number of different types of search. We're going to think about this. So let's, for instance, start with a breadth first search. In fact, for most purposes, we're going to be thinking about a breadth first search in this lecture, but I'll probably mention a few places where we could do something different, where something might be done in practice. So if we think about a breadth-first search in an undirected graph, so if we have a breadth-first search, and we think about the states that we have at any depth. So we're going to have the depth going across this way. What we have, and this would actually be like a log scale here, is if we think about each of these layers, that we have these growing layers as we go across this breadth-first search, and they're going to get bigger, and then eventually they get smaller again. Something like this. And so whatever the state space would be, you have some layer in the middle that is going to be the biggest layer that's going to be the most expensive, and this layer is really going to dominate the rest of the search that's going on. And so one thing is that we're not particularly modeling the state spaces as sort of exponentially growing in the same way that we did for something like IDA star. But the second thing that we'll notice here is we think about where duplicates occur in a state space where we have undirected graphs. Then if we think about when this state generates the successors of a state here could be in the next layer, they could be somewhere else in the same layer, or they could be in the previous layer, but they can't be anywhere else. And oh, sorry, the other thing is not only, I should say this, not only undirected graphs, we're also going to think about uniform cost edges. There's some work that's looked beyond uniform cost edges, but in the amount of time we're going to spend here, just a single lecture, we won't have time to go through that work. So I have some particular state that I'm thinking about here, and I'm wanting to reason about, where are the successors going to be, because we're worried about duplicate detection. This is the key thing that we're worried about. So if I have a state that's at some particular depth, it's going to be generated for the first time at the previous depth. That state will be generated. And then when it's generated here and we generate successors, some of the successors of this state could go back to the previous depth. Some of them could be states, that are reached by two different edges. So you could imagine having two different edges going to both a state and a successor. And the state and its successor happen to be at the same depth. And then, of course, we could have a state that is in the next depth. But that says that there's this key property that when we're doing a search, we really have to think about the previous depth, the current depth, and the next depth. And that's what the duplicate detection process in the middle of search has to worry about. So that's the key thing we want to keep in mind as we start to talk about search algorithms and we start to talk about external memory search algorithms. And now we're going to talk about some other characteristics related to this. So for instance, just something to take note of is, so this is more characteristics. Well, I'm going to put a break here. These are just sort of more, we have some features up above. There's some more features below. So for instance, disk is, and this means spinning disk, has actually, if you think about sequential access is fast. That is, once I find the location on disk that I want to read from, and I start reading, then I can read a large amount of memory very quickly. And in general, this holds for solid state drives. I can get my random access to work a lot faster, but when I read, I can actually read a lot of memory very quickly, and then I can do something with that much faster than doing a bunch of random accesses. And so, for instance, reading a bunch of memory that's sequential, as opposed to reading sort of one bit at a time or one byte at a time randomly, doing the sequential access is going to be fast. Something that we should be aware of, although these days you can, for instance, pay to get different quality here, but solid state drives actually have a limited write capacity. And this is something that maybe in the future isn't going to be as big of a deal. But if you were doing tons and tons of writing on a solid state drive, it can run out faster than a regular hard drive can. But part of this is just purchasing, because if you buy a cheap hard drive, that drive can start to have failures that it's just not as robust as buying a high quality server grade drive, something that's designed for being in a data center where it gets lots of writing and reading from it. And so we just have to be careful if we're going to do these sort of algorithms and you try to run them on commodity hardware, you might start to see a lot of failures. So these are things we have to keep in mind or just think about here, about the capacity of our hardware. And then if we're thinking about our types of search, there's two types of search we could be thinking of. We can be thinking about search for properties of a state space. Okay, and this might be, for instance, the diameter or the approximate diameter. So I might want to know, for instance, from a given start state, how many moves can I take before what's the maximum number of moves to get to any state optimally? And so this is, for instance, called God's number in Rubik's Cube. In Rubik's Cube, it was shown through some sort of exhaustive search that the answer here was 20. There is no Rubik's Cube state that requires more than 20 moves to reach. And that's actually from any state to any other state. It's always no more than 20 moves. So that's an interesting property. And that's something that you compute. And once you've computed it, you don't require any additional computation. Or you don't need to save the results around. You just get the results and then you announce, yes, the answer is 20. And then you'd be done with that. Of course, you might want to do more than that, but that's something like this. We also might want to know, for instance, what state is farthest from the start. So I'm not necessarily interested in the sequence of states that I get, but just tell me what state is farthest away. And so if I'm doing a search for this, I'm actually not having to keep very much information about the search around. And I can do these types of searches much faster than a breadth first search. Where I label the distances. Now, there's some really interesting work that can be done where you use a search that is designed for finding the properties of a state space and still can reconstruct a path out of it. And these sort of searches work by basically trying to find an intermediate state on the optimal path. And when you get a state that does that, you basically recursively reconstruct the optimal path in a state space. And this can be done very effectively. I'm not going to have time to talk about exactly how this algorithm works, but it can be constructed from some of the things that I am discussing in this portion of the lecture. So these are two things we're going to be aware of these approaches here, and we're going to be looking at both of these, how we can do both of these in the lecture here. One other thing of background, the last thing of background that we need is this idea of an implicit versus an explicit representation. Okay, and we've discussed this a little bit earlier in the class, but we'll really discuss it here. And the idea here is that if I'm going to be doing a really large search on a state space, and I'm going to enumerate the entire state space, I actually know, like every state is going to have a number corresponding with it that is what's called a ranking, and we'll get to this when we talk about heuristics in a few lectures. But every state is going to have some sort of ranking or value associated with it, and these are unique. There's a unique mapping, like a perfect hash function. In mathematics, it's a ranking or unranking function. And so the idea here is if I'm going to be searching the entire state space, I could be using an implicit representation. And what an implicit representation means is like its location in memory identifies the state. And an explicit representation means I just have like a full representation of the state. So that could be an array, or it could be some other ID or a rank. like a hash. And these would be two different ways of representing things. And so what happens here is there's a trade-off. If my state space is really large and I'm going to be searching a smaller fraction of that state space, then I probably want to use a full representation of that state space. And I'm going to use that full representation because the state space as a whole, I'm never going to store. It's too large to store, but I can store some smaller portion of it. And that's what we do in a state space like Rubik's Cube or something like that. There's 10 to the 19th states there. And so that's just too big to be able to store all of them on a disk on a personal computer. An implicit representation is used for a state space that is large enough to have some representation of it fit on disk. So maybe I've got 10 trillion states. And if I need a byte for each state or something like this, well, and we'll talk about this, but the idea is that if I have 10 trillion states, I can have 10 terabytes of disk, and the location on disk tells me what state I have. And now I only have to store the information. For instance, if I'm wanting labeled distances, then if I have an implicit state representation, then I don't have to store both the state and the labeled distance. I can just store the labeled distance. And so this is where an implicit representation, if I'm storing something that is close to a large fraction, or that is a large fraction of the entire state space, then the implicit representation allows me to avoid storing the state space. And just to be clear on this, the idea of an implicit would be like, I've got an array here, and then each of these locations here correspond. Maybe if this is a sliding tile puzzle, we'll do a 2x2 sliding tile puzzle. Then, this is 0, 1, 2, 3. This one might be 1, 0, 2, 3, and so on. And so every state here would correspond to an actual state up here, but I wouldn't actually have to store the 4 values, 1, 0, 2, 3. I'd just be able to store some value, like this is 0. That's the start state. Okay, so this is really important, and we could think about, there's other state spaces you might think about. If you don't understand this, of course I can't answer questions right now, but this is going to be really important, because many of the searches we're going to look at are going to use an implicit representation, which means the location in memory is identifying a state, not the full representation of the state itself. Okay, so we're going to then look at two pieces here. We're going to look at a search where I have an explicit representation and I'm trying to do a breadth-first search on disk, and we're going to look at what some of the approaches are for this, and then we're going to look at how we do it with an implicit representation. Okay, and to give you a sense of what we can do here, the 4x4 sliding tile puzzle was exhaustively explored using a external memory breadth-first search using an explicit representation. I think this was done all the way back around 2005 by Rich Korf. And so that's a really large problem. Today that's not too bad to be able to store in memory. We can very easily have the memory to do that. But at the time, that was really pushing the technology of what could be done. And so that's something that we might think about doing, is like, how could you understand the state space for something like the sliding tile puzzle? Okay, and so the idea here is we're going to look at a general breadth-first search. So this is going to be a breadth-first search. We're going to be thinking about an explicit representation here. And what we're going to have is we're going to start out imagining that it's simple, and then we'll show how we can do this a little bit more complicated. So let's think about right now that we're going to store all the files. We're going to have files. We're going to store every layer in one file. And so what we would do is we would expand. Actually, so let me start one step back. Okay, explicit search here. Sorry. Okay, so the first thing we're going to do is we're going to put the start state in file 0 because it's depth 0. And then for each depth d starting at 0, what are we going to do? We're going to expand all states in file D. And the simple thing here would be, ideally what we'd say is we're going to put the successors in file D+1, and then we'd be done. Right? In theory, we could do that. Just expand D, put the successors in D+1, we expand D+1, we put them in D+2, and you just repeat this process until you were done. But the problem is, of course, we have duplicates there. So we're going to need to take this step here, and we're going to need to move it down. And so now what we need to do is check for duplicates. And the duplicates could be in several different places. In particular, they could be at the previous depth, and they could be at the current depth. Okay. And so if there's no duplicates, then this is easy, right? We just expand all the states in file D. We put the successors in D+1. Now, just to be really careful here, if we look back, what did we say the properties were up here? Spinning disk, sequential access is fast. So for something like this, what am I doing? I sequentially go through the file D, whatever one it happens to be. I read the first, I read them. And I'm not going to actually read one state at a time, but I might read, 1,000 states at a time or 1,000,000 states at a time. I read them. And then as I read them, I'm going to, I'm going to take those states and I'm going to expand all of those in a row. And then I would be, writing them out to the next disk. And when I got all of the successors, I could write them all out at once. So that's going to be a very efficient operation. So this breadth-first search, as we've described it here, is doing this sequential access. And there's no random access at all. So this is what makes something like this efficient, and why this general approach for a breadth-first search is going to work in practice, or is going to be is general is going to try and work. But what we're going to have to do is we're going to have to figure out how to get rid of these duplicates, and there's a couple different ways that we can do that. So in general, this is called duplicate detection or delayed duplicate detection, and so we don't want to necessarily do this immediately. And avoiding to do this immediately allows us to make this process much more efficient. And so generally what we're going to do is there's going to have some sort of delay in here to make this efficient. Okay, now there is a way that we can do this that tries to make sure that there are no duplicates at all. Or in particular, we can make sure that there's no duplicates within past layers. So I'll go ahead, we'll go over here. So this is called frontier search. And what frontier search is basically, it's going to maintain information about the frontier so that it avoids going backwards. And so what we're going to do is every state keeps a list of operators that have been used to generate the state. So for example, in the sliding tile puzzle, there's only 4 operators that we ever have. So that's going to be very inexpensive. Therefore, with 4 bits, what we can do is we can say up, down, left to right. Did I reach this state by up? Have I reached this state by down? And if I've reached by those ways, then for instance, now I'm only going to generate new successors to the left and to the right. And so if I'm able to mark states in that way, then what happens is when I go and try to expand a state here, as I expand these states, I actually know in the previous layer where I actually reach states. Now, there could be duplicates within the current depth. And so this is something I would have to deal with. And there's a number of ways you can deal with duplicates in the current depth, but I'll explain those in a second. And then when I generate the next depth, I'll generate the next depth with possible duplicates in there as well. But the point being is that there's also, in the sliding tile puzzle, there's a parity of where states are reached at different depths. And so that makes things a little bit easier because you get certain type of duplicates. You don't get certain type of duplicates in the sliding tile puzzle that you can get in other state spaces. So, okay, so if we think about this, the frontier search, the idea is we're going to keep a list of operators that have been used. And so with every state, we have an explicit state representation and an explicit list of operators that are forbidden because they'll take us back into states that have already been closed. And what frontier search allows us to do is it allows us to only keep the current depth in memory, and we don't have to worry about going back and checking previous depths. But again, this is only going to be effective with a state space that has a uniform cost edges and undirected graphs, and that's what we're looking at in this context. So if you can do frontier search, in Rubik's Cube, there's 18 moves, so we don't necessarily want to keep 18 bits around to do this for Rubik's Cube, but for sliding tile puzzle. And there's a few other state spaces, but something that has a very low branching factor, frontier search is going to work. Now, we still have to think about how do we check for duplicates between the previous depth and the current depth, and how am I going to do this? How am I going to take care of this? And the idea here, even if we think of it in the context of frontier search, there still could be two states that are generated from two different parents. And so I get a particular state, and one state has been generated, let's say, with up, the other one has been generated with right. And now I have two states that have different parents, and I want to merge them together and say, oh, this has been generated by both up and right. And so now I want to only think about the down and left operators to apply from there. So how am I going to do that? Well, so what do I have here? I'm searching in my space. I have a file here, which is, let's say, depth 0. Let's just say depth k. And then I've generated from here a bunch of states, some of which may be duplicates at depth k plus 1. So what we want to do is we want to be able to find what are all the duplicates that are sitting inside a file here. And remember, this file is written to sequentially. So every time we expand, we're just dumping states into this file and just putting them in there. We're not trying to read and do anything else with that. So for duplicate detection, there's a few things we can do. One would be sorting based. And for sorting based duplicate detection, what you're going to do is you're going to take your depth, take your file, sort it, and there's all sorts of algorithms that have been designed for doing external memory sorting. It's not, this goes back even to punch cards and things like that. When memories were very small, then obviously on older computers, you would do a lot of sorting on disk. But you're going to take a file, you're going to sort it, and then all duplicates are next to each other. So all the duplicates are adjacent, and then we can simply do one read through the file sequentially, and we can merge all the duplicates. And even at the same time, we could then expand those states and write them into depth k plus 2. So sorting based is basically you've got this file of all your successors, take all your successors from the previous layer, sort them, and then read through, find the ones that are adjacent will be the same state. And you're only sorting by the state. You're not sorting by for instance, by the operators in your frontier search, or if you're just doing a regular breadth first search, you'd just be sorting them. And then the other thing is that if I have a file, so when I'm done with that, I have my layer sorted. So if I'm not doing a frontier search and I'm just doing a regular breadth first search, when I finish each layer, that is when I start to read the next layer, I will actually be sorting that layer. And now, given that it's sorted, it's actually very fast to compare one sorted layer to a previous sorted layer on disk. I can read through those sequentially, and I could remove any states that were duplicates from previous layers as well. Okay, so sorting-based duplicate detection, a lot of this gets a lot easier. And basically, we're taking a file, we're sorting it, and then we're always comparing sorted files and removing duplicates from sorting. So that works, but there is sort of this log overhead to sorting. And so another approach that's very common here is hash-based. And hash-based duplicate detection is going to split a file or split states into files according to a hash. Sorry, my handwriting's a bit messy today. And let's put it up here. I can write a little bit clearer at the top of the screen than the bottom. And then we're going to put states into a hash table. And we can use a hash table to detect the duplicates. Okay, so the idea here is that we could think about it both in the context of frontier search or in a general breadth first search. In frontier search, what we'd be doing is we only have to detect the duplicates at one particular level. And so what we're going to do is we're going to choose part of our state. For instance, we might look at the first 5 bits of the state space representation, and we're going to break it into, if those bits could all be set evenly with even probability, we'd break it in something into 32 files. So we might, and this could be done, there's a number of parameters here you can do, but so we might write out 32 different files based on the hash function. We might write to one file and then later break that file up. And we're not going to worry too much about those details, but the idea is now I've got a bunch of different files based on the representation of the state. And we know, because we're going to use the hash, so we're using the hash to decide where a file goes, and all the duplicates will have the same hash. So they're all going to go into the same, file here. And now I can load one of these files. And because the files are smaller, ideally I'm going to be able to afford to load one of these files into memory. I load all those states into memory, and now I can do all the duplicate detection, and then I can write those states back out, or I can expand them and go to memory. And so here, if I'm doing this within the frontier search context, I'm only having to do the duplicates at one particular layer. And so after I'd written them all to this layer, which would actually be many different files down here, then I would, when I'm ready to start the next level, I would then load this file and do all the duplicates. And that is the key here. Maybe I didn't make this clear before, but the key, and this is where the delay comes from, is that you don't immediately find duplicates when you generate the states, which is what we normally do with A star. In A star, right, we look it up on the open list. Here, we're just going to generate and dump it on a file on disk. And then when we're ready, either when we're done with the previous iteration or we're ready to start the next iteration, then I go ahead and load this file and remove all the duplicates. And it's very effective to do this all at once, as opposed to trying to do it one at a time when they're found. And so that's how we're going to make it inexpensive enough to be able to do this. So here, in the context of frontier search, you would just take this layer, you'd have your files here, and you'd load them in. If I'm doing this in just a regular breadth first search where I need to compare to the old files, what I would do is I'd load in to get the duplicates, and then I would load one of my old files. So here I'm comparing against the previous depth, maybe even the current depth. I can load those other files, and I can just, for each of those states, I hash them. If that state is in the hash table, then I remove it from the hash table. Because I say, this is a duplicate from a previous layer, I can go ahead and get rid of it. And so when I'm done with that process, I'll have a set of states here with all the duplicates removed from previous layers. And then I can go ahead and expand all of these states, write them out to disk for processing at a later point in time. Okay, so that gives us a breadth first search, explicit breadth first search. The idea is we're going to take all the files at depth D, or the file for particular depth D, and then, multiple files if we're down here. We're going to take the file, we're going to expand it, and we're going to think about checking for duplicates at the previous depth or the current depth, but we're going to delay that process. If we're doing a frontier search, then I only have to check at the current layer, the next generated layer. So I'm going to expand all of them into this file, so there may be many duplicates in this file, and only when I'm done do I go and remove all the duplicates, when I'm ready to do the next layer. When I'm wanting to do, if I'm not doing a frontier search, but just a general search, I can either sort my files or I can put them into separate files based on their hash function. And then when they're sorted, it's easy to take 2 sorted files and remove duplicates. And with a hash-based implementation, it's very fast to compute the hash for each state, and then to find duplicates based on hash collisions there, based on the original state. So if we do this, then this will allow us to get through our state space and find our duplicates. And I just want to point out that there's another, it's basically a hash-based method, but this is something that allows us to do this in parallel more efficiently. So something I haven't said here is that many of these operations we can run in parallel. For instance, if we share writing to a disk, we can have 2 different threads or many different threads that are expanding the states here in parallel, and then write them out here in parallel. And that's all going to give us really nice speed up when I try and do a large parallel search. And so, so this is something that's very commonly done, and it's very useful to think about this. And so if we think about here, sorting can be done in parallel. The hash lookups can all be done in parallel. And now we have to be a little bit careful about how this is done. And so there's another approach here, which is called structured duplicate detection. And this is something that's thinking about the parallel nature of the search. And it's also thinking about where successors are going to be. And with the structured duplicate detection, we can actually avoid some of the delay that occurs here, because we're going to be very careful about the way that our files work. And by being very careful about the way that the files are being used, we are able to use them essentially more effectively. And let me give an example of how this works. And the key thing here, just to point out, is that inside this file, there can be many, many duplicates inside here. And if I have too many duplicates, then the memory that's required to store all the duplicates in here could be actually quite extensive. I might run out of disk. So many of these algorithms, what happens is as I'm doing this search, if I run out of disk, I might have to go and take all these files and do some sort of duplicate detection on them to reduce the size of those files so that I can continue my search. And exactly the same thing down here. All the duplicates are sitting inside these files. I might have to remove those duplicates. So structured duplicate detection is a way that tries to avoid having to do that. And it uses an idea of a scope of where the duplicates can occur. And we're going to illustrate this on the sliding tile puzzle. And so I'm going to use a larger sliding tile puzzle here. We'll do the 3x3. And so imagine here that the blank in some state that I'm looking at is in the upper left-hand corner. When I think about this state and think about generating successors and wanting to find duplicates, what I know is actually all of the successors of this state are going, and even the predecessors of this state, are going to have the blank in one of 2 locations. And they can't be anywhere else. Similarly, I have another state down here, and let's say it's a green state where the blank is down there. And I ask, where could the successors of this state be? Well, they can only be here, and they can only be there. And so what I can see, in fact, if I wanted to be just a little bit more efficient on this, we can even do this. I could put the blank right here, and the successors here could be both here, and inside here. So what we see is the process of expanding the states that have the blank in this corner and generating the successors, and even looking up in previous iterations what are the successors and doing duplicate detection, is entirely independent of the process of a state down here. And so if I possibly can do this, if I, for instance, know that I have a small scope of where my duplicates appear or where my successors appear, then what I can do is I can actually say, well, we'll write this in red. So I'm going to say, look, I'm going to load all of these states into memory, and that's where all my duplicates are going to appear. And when I want to process the green state, I'm going to get a lock basically on these states and say no one else is allowed to write to those. I'm doing it, and I'm going to load all of these into memory, and I'm going to do all my duplicate detection, as I expand this state. And so I've immediately removed duplicates. And I can do this because the scope of where the duplicates occur is a small enough scope that it becomes very efficient to do so. And then similarly over here, we'll use a different color, but over here I can say, look, I need these two sets of states. And let me just say really carefully here, all I'm saying is it's the set of states where the blank is in this location. I'm not saying anything else, right? So the numbers that are in the tiles could be anything. But so there's potentially, well, in this case, not millions, but on a larger sliding tile puzzle, you could imagine there's millions of states with the blank in this location, and there's millions of states with the blank in this location, but that's much smaller than the entire state space. And so I can very effectively load these little pieces in the duplicate detection scope. I can process successors of this state by looking up duplicates and writing them to appropriate files for the next step. And I can do this entirely independent of some other piece that's working over here. And if I have a granular enough of an abstraction of my state space, then I'm able to do this. I might be able to only require a very small fraction of the entire state space while I do this entirely in parallel. So this is a very nice technique that can take advantage of the type of structure that shows up in our state spaces. And there's some very nice work that was done about 15 years ago that looks at how this can be done in planning. This is primarily by Rong Zhou and by Eric Hansen. And just to say, to point out here, so we could be doing this on, larger sliding tile puzzles, for instance. But the other thing we could be doing is we don't only have to say where the blank is. So right here, there's 16 locations where the blank could be, but I could say, actually, I want to know where the blank and the 3 is. And so I could say, well, my state representation is, the location of the blank and the location of the 3 tile. And so when I think about those two locations, I still know that when I move the blank, the 3 tile is going to be in the same location. That doesn't move, but the blank is going to go to one of these states. And depending on how many of these other states, maybe I also want to have the 7 tile. So by saying my duplicate detection scope is going to depend on where the 3 is, where the 7 is, and where the blank is, then I'm going to get a much smaller duplicate detection scope. And I can load these sets of states fairly efficiently, and I'm not going to have many collisions. It's still going to be a small fraction of the entire state space. Okay. So structured duplicate detection is a hash-based duplicate detection where it takes advantage of the structure of the state space to know where the successors are going to be and to know that the files in which the successors occur are small enough that we can load them into memory and do the duplicates immediately as we generate the states. And the other thing here is that there's many, many states. In an ideal case, there'll be many, many states that all follow the same abstract pattern. So I can actually expand like 10,000, a million states at once that all according to this plan. And therefore, the cost of loading up the duplicate detection scope is amortized. That one-time cost of loading it is amortized. Then I get to do the duplicate detection in memory. It's very fast, and then I write it all out. So structured duplicate detection is like hash-based, but it's able to avoid doing the complete delay here by being very, very careful about how things lay out in the state space. And just to be clear here, structured duplicate detection is it's going to be very effective, and it does, as I said, it works very well in practice, and it actually is quite a generic approach. There's a number of complications that you need to look at to make sure that you can do this effectively, but it can be done, and it's going to find, like any of these other approaches, it's going to find optimal solutions. And so we're going to see in a couple lectures when we actually come to building heuristics that this idea here is very similar to the idea that's used to build heuristics. And so we'll come back to that. Okay, and so here, because we're standing in this lecture at already 45 minutes, I'm going to stop here in terms of looking at explicit search with breadth-first search, and also looking at the sort of some of the general ideas here of what happens when we want to do external memory search. And I'm going to start another video that will look at just the question of how we do search with an implicit state representation. And we're going to look at 2 algorithms that are related to that for an implicit state representation. So we'll see you in that next video.